Professor Archan Majumdar from S Bose Institute. He is an expert in dual fields of gravitational cosmology and quantum information science. He has published more than 150 research articles in reputed international journals. His significant contributions are in the domain of dark energy, gravitational waves, primordial black holes, quantum entanglement, non-locality, information processing protocols, and decoherence. He has delivered more than 100 invited talks on these and other topics in institutions and laboratories around the world. 20 research scholars have obtained their PhDs under his supervision. Professor Majumdar is actively engaged in development of quantum science and technology in India with 3 completed projects under the Quest program of DST. At present, he is a senior professor at SN Bose Center for Basic Science. So I invite Professor Majumdar to deliver his talk.
Yeah, thank you very much, Arun. Professor Arunpati is my good friend and very nice to meet you.
Thank you.
So I would like to thank the organizers for giving me this opportunity to speak here before such an illustrious audience, and some distinguished colleagues who are sitting here I'm meeting after a very long time. So it's a great pleasure for me to be here. So the talk today is about quantum uncertainty and and information theoretic applications. And I am from the S Bose National Center for Basic Sciences in Kolkata. And so what is the perspective of for today's talk? So quantum mechanics, as you all know, we are celebrating 100 years of quantum mechanics. And the founding pillars of it is one of the, the most important founding pillar of modern physics. And in the early 1900s, a few concepts came about, were discovered. For example, the most prominent ones being the uncertainty principle, which is the key focus of this work, and also the superposition principle. So these are key elements which brought about the so-called first quantum revolution, and that took place 100 years ago. But later on, starting from the late 1900s, 1980s, 19s, and so on and so forth, another new, domain of study was born, which is called quantum information science. And this was actually a result of serious work by people in quantum foundations and also elements of information science. So the study of quantum foundations played a key role in this development. And this has brought about the so-called second quantum revolution in the sense of its potential for bringing or ushering in entirely new range of quantum technologies. Okay. So now somebody will ask, after such a beautiful previous lecture, why do we want to, even bother about such mundane things as technology? So my answer would be as follows. Quantum technology are nothing but an expression of happiness of the furtherance of quantum mechanics. There are many beautiful aspects of quantum mechanics. And how does a scientist or a practitioner feel happy about quantum mechanics? That is by discovering more and more new elements of manifestation of quantum mechanics. So it is again a furtherance of happiness, as our previous speaker was trying to highlight. Okay, so basically what is quantum information science? So it is nothing but the theory and practice of accomplishing certain physical tasks which are not achievable using the laws of classical physics. And this involves storage, transfer, and manipulation of information which is contained in, now we are doing physics, so the information has to be manifested through physical degrees of freedom. And physical degrees of freedom of what? Elementary particles, or the so-called quanta. Okay. And all of you young students who are here immediately realize that there have been lots of developments in the last couple of decades on quantum key generation, okay, secret key distribution, quantum computing, quantum teleportation, so on and so forth. Okay. So these are indeed now being practiced and not just in the realm of theory. For instance, let us take this aspect, just a sort of giving an example of quantum teleportation. And I'm sure this has been talked about in the conference, just to give a quick recap. So if you have an entangled pair of two objects or two particles, and these can be shared by two distant parties, and the party B can have some original quantum state, and the task of him is to transfer this to a distant location with party C. And this can be accomplished by using this resource of an entangled pair of objects. And as a result, because of the no-clouding theory of quantum mechanics, the original state gets destroyed at this end, whereas it is created at the other end. But again, remember, there is no faster than light communication. So in fact, party A, it is an essential part of the protocol for party A to send a classical signal to the distant location. So no violation of special relativity is taking place. So this is nothing but a replication of an unknown state at a distant location. And this is no longer science fiction, was proved in fact 20 years ago. And these days people are actually indeed teleporting states from the Earth to artificial satellites. And this is not just amusement value, this is also useful in the sense of technology, and that is through, say, distributed quantum computation. Distributed quantum computation can only happen when teleportation takes place. And I just, to give you an example, highlight of our work of ours, which was done 15 years ago, where we showed how such teleportation could be actually observed in the lab. And this is nothing but the formalism of entanglement witness operator for quantum teleportation. And just again to advertise its importance in various domains, people have worked in theories even like boson sampling using such witnesses for quantum teleportation. So this was just an example. This is not the main part of this talk, so excuse me for this. The main focus of the talk is trying to connect a fundamental aspect of quantum uncertainty with quantum information processing. So the question one asks is, what is the role played by such a fundamental thing like quantum uncertainty in the very new beautiful tasks of quantum information processing, like computation, secret key distribution, and teleportation, the example of what I gave you. Okay. So the idea is, let us to begin with have a very quick recap in this short talk of what is the uncertainty principle, and this I would again in just 30 seconds or so give you a textbook, formalism of uncertainty. So if you consider uncertainty of an observable, in this case, let us take A. So typically you measure the standard deviation, which is denoted by delta. Okay. So again, all students would realize this is nothing but the difference of the expectation value of the square with the square of the expectation value. Okay, and I can denote this A minus average of A by this curly A. Now, if you consider two self-adjoint operators, that is A and B, and you construct a product like this one, and by its definition, it is positive, semi-definite, greater than or equal to 0. And now if you see that you can, if you try to minimize, if you can try to optimize this relation, immediately one gets the bound on lambda, and this turns out nothing but the commutator. Okay, so lambda turns out to be nothing but the commutator of these two observables. And so for instance, if you have canonically conjugate pair of observables, so slide is actually moving slower than I would intend to because it's a very short talk. So if you have a canonical, canonically conjugate pair of observables, for example, you get back the Heisenberg uncertainty relation. That is, if you say x and p, that turns out to be greater than or equal to h bar by 2. So this is the very basic textbook formalism of quantum mechanics. And most people who actually even pursue physics as a career, even do a lot of beautiful works in many other domains of physics, learn nothing more about the uncertainty principle than this. Okay, so that is enough for them. However, people like us who are interested in foundations and information theoretic applications know that there has been a lot of development in this subject over and above what Heisenberg and initial forefathers did. So let me come to some of them, and let me then try to connect it with some foundational and information theoretic concepts. So first of all, I take this example of the EPR paradox, which has been talked about at length in this conference and also in the wonderful lecture by Professor T.P. Singh. So how does one, EPR paradox is there, but how does one demonstrate it or observe it or verify it in the laboratory? So that is again nothing but through the uncertainty relation. So again, let me just skip through these slides regarding the basics of the EPR paradox. That had been because I didn't know that Professor T.P. Singh was going to talk about it. So I actually kept it in my talk. But the essential element now I would like you to concentrate on is that, no state in quantum mechanics has the property of a predetermined definite position and momentum. Why? And why did EPR conclude that QM gives an incomplete description of the state of a particle? Because this is in direct contradiction to the uncertainty principle or uncertainty relation. Okay. So this argument follows on using the uncertainty relation. If there was no uncertainty relation, this argument would not logically follow. So that is the main upshot I would like you to consider here. Now, regarding the question of demonstration of this EPR paradox. So how was it first demonstrated? It was done through a beautiful proposal by Margaret Reid way back in 1989. And this proposal, since at those times it was difficult to do experiments with isolated single particles like electrons and photons, what they considered was they considered quadratures of electromagnetic field. So I defined for you quadrature like x theta and y theta, y phi. So again, those of you who are interested, I would like to, may discuss it with me later, the technical details. But for the moment, just think of this, that these are, again obey, these are creation and destruction, annihilation operators. They obey quantum, they obey commutation relations. Okay. And now, using the EPR argument, you can try to infer the property of one quadrature by measuring the other. Okay, so that is the essence of the EPR argument. So, for example, E theta 1 stands for the estimated value, E stands for estimation, estimated value of this x quadrature if you actually measure the y quadrature, okay, with these settings. And you can do so with some accuracy, which are labeled by G1 and G2. Now, what these people, what Margaret Reid in fact proposed was that using such an estimation, using the EPR argument, you could formulate another something like inferred uncertainty. Okay. Now, this inferred uncertainty is, if it obeys the actual uncertainty principle, then you do not get anything like the EPR paradox. But however, if you actually do this experiment and measure these objects, then you would see that this inequality is indeed violated, and they are violated due to the presence of quantum correlations. So this in fact is a demonstration of the EPR paradox, and by the way, these are inferred uncertainties. So there is no actual violation of the Heisenberg uncertainty relation. So this first experiment was done way back in 1992 by Au et al. Okay, so far this is one application of uncertainty in foundations, that is the EPR paradox. But now let me move on to the literature, the further developments in this theory of uncertainty relations. So as you see that the quantification of uncertainty is done through the object, the mathematical object of standard deviation. Okay. And so this leads to some not paradoxes, I would say, but some not really inconsistencies even, but it leads to some kind of, lack. So what is that? Some kind of problems. For example, if you look into this Heisenberg uncertainty relation, and on the right-hand side, if you consider the eigenstates of this operator, so you will get a very trivial relation, that 0 greater than or equal to 0. Okay. So indeed, it was felt that there is scope for improvement, and to make this bound more optimal, and various kinds of relations were proposed even by co-workers of Heisenberg, that is Robertson, Schrodinger, and so forth. So I would like to first of you to focus on this relation, which is due to Robertson and Schrodinger, which introduced, in addition to the standard commutator, another anti-commutator term on the right hand side, or if you take everything together on the left hand side. So the additional anti-commutator term, as introduced by Robertson and Schrodinger, actually optimizes the bound of uncertainty. Now, I have no time to go through the derivation, which is also, follows upon using Schwarz inequality. It's not at all a difficult derivation. Now, this sort of improvement, okay, improvisation in the uncertainty relation leads you to enable one more very fascinating task, that is discrimination between pure and mixed states in quantum information. Because in quantum information, pure states play a very, essential role, significant role. And we do not want, in most applications, except for some, that the state to be get degraded by the influence of the environment. So how can one differentiate between pure and mixed states? So this was proposed again by ourselves, our group in SN Bose, with a couple of my students, and that is also long ago, again 12 years ago. So we proposed, let us take this expression for Robertson-Schrodinger uncertainty, and then if we choose suitable operators, so that we can actually say that for some such operators, for pure states, this expression of uncertainty will be 0 exactly. However, for mixed states, this will be greater than 0. So then we will be able to discriminate between pure and mixed states, something which can be realized in experiments. And not only that, we can give a measure of mixedness or measure of purity through this Q, whenever it exactly equals to the linear entropy. And those of you who have studied quantum information know the linear entropy is a measure of mixedness. Okay. So this is another expression, but let me move on to something else, and that is the work of our chair, Arun Pati. Okay. So again, about say 10 or 11 years ago, Arun Pati, in collaboration with McCone, proposed that let us take standard deviation as a measure, but instead of using product of variances, let us take the sum of variances. Okay, so this is in form a sum of variances, and if you take a sum of variances, then at least your uncertainty relation is tightened. So this was their PRL work in 2014. And not only that, this was a work which was of fundamental importance in quantum theory, but we can also use it in quantum information to enable or to demonstrate another aspect of the EPR paradox, and that is called quantum steering. Okay. So again, in this workshop, in this school, you will have a lecture on quantum steering. So I will not say much about quantum steering, but just to say it is an expression, a practically demonstrable expression of the EPR paradox. So we showed how quantum steering can be revealed using this Makone-Pati relation for certain states when the standard Heisenberg relation is unable to reveal such steering. Okay, so now let me move on to, so now let me again go back to the general form of these uncertainty relations. See, both these relations, that is the Robertson-Schrodinger and also the Makone-Pati one, which involves variances, one in the product form, another in this sum form. In there, the measure of uncertainty is quantified by standard deviation. Okay. So can we do better? Is there some other measure of uncertainty? So certainly the answer is yes. And there are certain problems with such measures based on standard deviation. For example, standard deviation is a mathematical expression only up to order 2, right? But there can be correlations in quantum states which are revealed only in higher order. So higher order correlations are not revealed by these measures of variance, right? So one can go beyond standard deviation, and this was realized again 50 years ago in terms of something called the entropic uncertainty relation. Okay, so I don't have the reference here, sorry, I should have put it up, but this is work of 1970s and 80s, many years ago. So in this case, what those people told us that let us go deeper and let us try to quantify uncertainty by another fundamental quantum aspect, and that is related to probabilities. So in quantum experiments, you are actually measuring probabilities of occurrences of outcomes. So if you use probability directly, you can quantify average uncertainty using entropy functions. For example, H denotes the Shannon entropy. And then you can see the right-hand side is nothing but actually the overlap between your probabilities obtained through, say in this case, orthogonal setting of the different apparatus. Okay. So this quantifies the incompatibility of your measurement settings. Okay. Or in other words, this factor quantifies the complementarity of observables. So this is another way of measuring or quantifying uncertainty. And then this gave about two further demonstrations of the EPR paradox using, say, other very important states like non-Gaussian entangled states. And this is a work with Professor Girish Agarwal, whom you all know is a very famous quantum optics practitioner, now based in the US. Okay, let us move on, now come to another manifestation of uncertainty. So far, what we have talked about is average uncertainty, where average is taken over all measurement of outcomes. Okay. So now in 2010, there were these two smart people, Oppenheim and Wehner, who told us that there is another way to actually quantify or understand uncertainty, not in the coarse-grained sense, that is to take average over all measurement outcome, but consider a particular outcome or just a combination of a few outcomes. So what is this? So they labeled it as fine-grained uncertainty relation. So in this case, to again repeat, the uncertainty of a particular measurement outcome is considered, or a particular combination of measurement outcomes. And this is an improvement over entropic uncertainty, in the sense that though again we use probability to quantify uncertainty, this is a probability of a particular outcome. So what is the advantage? Again, FUR, or fine-grained uncertainty, is able to discriminate between various no signaling theories. No signaling theories you also heard in the talk by Professor T.P. Singh. For example, when he was talking about the quantum bound on violation of Bell type inequalities. So you can go beyond 2 root 2 up to 4 when you are in the realm of no signaling theories. So various kinds of correlations are apparent in such no signaling theories, and application of fine-grained uncertainty allows you to actually pinpoint what correlations we are using. Okay. So these are some works which actually dealt with such applications of fine-grained uncertainty. So these are also old. Let me not spend too much time, but let me just spend half a minute on another beautiful aspect that is of quantum mechanics, that is called quantum memory. Okay. So what is quantum memory? It is a manifestation of quantum entanglement. So this slide is taken from a paper in Nature Physics in 2010. So suppose there is a person called Bob here, okay, who has one particle, two particles, and they are entangled. And one of these particles he sends to his friend Alice, who is here. Now, Alice can make a measurement on either of these two complementary observables, and she can note her outcome, and she announces her measurement choice to Bob. Now, the game here is to actually Bob to predict, or I mean, posteriori, not predict, but trying to decide what measurement Alice, what basis Alice chose, whether S or R, what one of these complementary bases. And what enables Bob to make an informed choice is nothing but his entanglement with the other particle, and that is called quantum memory. Now, using this quantum memory, you can precisely, or what you can do here, you can actually pinpoint the bound of quantum uncertainty. Okay, and that is what we did exactly following this work. So, okay, so what we did was actually use this quantum memory, and using fine graining of entropic uncertainty, we actually showed that the optimal lower bound of entropic uncertainty is revealed in presence of quantum memory. Okay, so now this work is not only, I mean, it has this foundational value, but an immediate application, those of you who are technology minded, is in security of quantum key generation, right? Okay. So again, if you are, this provides for you the best possible, most optimal bound that you can achieve in any given experiment. You cannot do better than this, and this is through the use of the fine-grained uncertainty relation. Okay, let us now move on. So what I'm saying again for young students, these are not just confined to theory. A lot of experiments have been done regarding these fine-grained uncertainty relations and quantum memory. So these are some examples, and as I was saying, they can be used for key distribution, secret key distribution. Again, the fundamental idea is the Einstein-Podolsky-Rosen paradox, nothing else. I mean, work from way back, but this provides you a sound basis for security in quantum key distribution. Okay, so in this way, basic science connects with modern technology. So that message is what I wanted to convey. Okay, so there are many other experimental implementations of fine-grained steering, and there are some examples. Those of you who are interested can look into. And this involved my student Tanumoy, who went to Paris and did this experiment of fine-grained uncertainty and verified our theoretical ideas. Okay, and there are experiments by other groups also. For example, this is an experiment by a Chinese group, again verifying this idea of fine-grained steering and optimizing quantum uncertainty. Now let me come back in the last, I think, how much time I have? I have 15, my talk is half an hour anyway. I've run through it like anything anyway. So maybe we can keep, maybe we can keep some time for discussions. 5 minutes, okay. You see, Arun is my old friend, so he was trying to give me 10 minutes extra, but never mind. So the last portion of this talk is, I mean, again connected with the earlier talk, but we try to actually think somewhat because we were all rushing through and trying to demonstrate some applications and connections. But let us pause for a while and try to go back to our mind and try to, again, coming back to the beautiful previous talk, let us try to think of some meaning behind what we are trying to doing. Okay. So the point here is that, so what is the, if we pose this question that quantum mechanics, as I said, has many beautiful applications in quantum information, and many revolutionary technologies have been born out of it. But can we pose this question that given quantum mechanics, can we identify any key feature or fundamental property which actually enables us to do such, perform such beautiful applications? Okay. In other words, what, if any, is the key difference in property between quantum mechanics and classical physics? Can we identify something, at least one such property? So what is the answer? So this question has been looked into or thought about by us, not only us, there are many other groups around the world who have tried to think about this element in the last 10, 15 years, since the time actually people saw these beautiful revelations of quantum information. And the answer I would like to convince you now, I mean, what is the answer? Can you tell me without looking at the last slide? Can some of the young students venture out with answers? Any key property in quantum mechanics which sets it distinctly apart from classical physics, which again allows you to perform such beautiful applications? Yes? Haritha says, of course, it is linked to superposition. I cannot give you no, but the answer is certainly not entanglement. Some people say entanglement. So you are correct. I mean, superposition forms the basis of entanglement generation, but I would want to go beyond entanglement. So I would say that the answer is the character of quantum measurement. Character of quantum measurement sets it distinctly apart from what you consider in classical measurements. And this is the notion of incompatibility of joint measurements in quantum mechanics, again a manifestation of the uncertainty relation. Okay. So I would say this, and now in the last few minutes, I would like to convince you why I'm saying this. Okay. And this also leads to another beautiful manifestation of such, say, superposition or character of measurements, and that is something called quantum contextuality. Okay. So why I say this again? Because let me say this, that people have heard about quantum entanglement, which is a very powerful quantum resource, but there indeed exists some beautiful task, in, at least in communication, quantum communications, which can be performed without the presence or use of any entanglement. And the primary example is this QKD, quantum key distribution, in the way it was very initially formulated by Bennett and Brassard, the famous BB824 protocol that involves no entanglement, but it does involve superposition, right? So these sort of scenarios are called prepare and measure scenarios, where you prepare the quantum state of a particle somewhere and you send it to a distant location, some other party, and then you perform tasks involving yourself and that other party without any entanglement anywhere coming in. Okay. And the main manifestation of this is in the so-called quantum random access codes. So randomness has also been talked about in this conference. So at least for young students, I would like you to study and read this, the subject of quantum random access codes, how it is generated. It informs you regarding some very key properties of quantum mechanics. Okay. And now, so these are indeed based on some non-classical properties, some non-classical correlations, certainly not on entanglement or spatial correlations, but what kind of correlations? Temporal correlations. Again, temporal correlations is a subject which was in a main way introduced in quantum mechanics by the work of Leggett, and Leggett was the speaker here. So he formulated some inequalities akin to, Bell-like inequalities, which are called Leggett-Gerg inequalities. So in the same way that you can test Bell inequalities, you can also test temporal correlations using violation of Leggett-Gerg inequalities. And these are nothing but they have one-to-one correspondence with quantum random access codes, as we showed in this paper in 2022. So this is titled Role of Non-Classical Temporal Correlations in Powering Quantum Random Access Codes. So this again brings us, actually, this answers in a way that what causes quantum advantage in quantum communication tasks without entanglement. So even in this case where there is no entanglement, it is indeed the character of measurements that you employ in the test of Leggett-Gerg inequalities, as Professor Dipankar Om is sitting here, he will also vouch for it. The character of measurements you employ here will lead you to reveal the presence of such non-classical temporal correlations, which can also be viewed from the point of view of random access codes. So it is nothing but the manifestation of measurement incompatibility. Okay, so this is one thing, but finally, about 2 years ago, we very clearly showed in this work of ours that measurement incompatibility is something which will lead you to direct advantage in quantum communication. So you can give me any scenario, any experimental setup where you have such incompatible measurements, and I can give you the exact analog of it in your communication advantage. That is some communication task which is more advantageous than an analogous classical communication task. And this is a two-way relation. So if you give me some example of quantum advantage in communication theory, I can immediately tell you that there indeed exists at least a pair of incompatible joint measurements. So this is a two-way connection. Okay. So now finally, let me just go to, in the last 1 or 2 minutes, the role of contextuality, which also follows from this case. So what is contextuality? Okay. So we were talking of quantum correlations, and be it spatial correlations or temporal correlations, whatever correlations, but for certain correlations, there is no probability distribution which is in agreement with marginal distribution, which corresponds to set of compatible or jointly measurable observables. So in a nutshell, quantum contextuality is just a manifestation of such correlations where there exists no such probability, I mean, in marginal distribution, no such marginal distributions which are in agreement with the overall distribution. Okay. So this is contextuality. But this is not a very intuitive definition of contextuality. This is a mathematical definition. But if you would like a sort of more intuitive understanding, a very heuristic understanding, you can think of it like this. So for example, of all fundamental properties in nature, you can classify them in two different ways. So one is an attributive property, which is there irrespective of measurement. So for example, for fundamental particles, you can have, like it was talked about again in the last lecture, you can have electric charge, less mass, so on and so forth. So that the electric charge of an electron stays itself, whether you measure it, see it or not. It is an attributive property. But on the other hand, a contextual property is such that it is only revealed in specific experiments and under particular conditions. And this characterizes the interaction of the object with the external world or measuring apparatus. So you can immediately think of spin projections, probabilities, so on and so forth. And this again leads us to the role of measurement in quantum theory. Okay. So this role of measurement in quantum theory sets apart quantum contextuality completely different from notions of classical contextuality. For example, you can think of a chameleon and its various colors, but this is completely different in quantum theory, okay, because of the nature role of quantum measurements. Now what happens is that there are a number of applications of quantum contextuality in many information processing tasks like random state discrimination, computation. So there is a famous Nature article also, again 10 to 12 years ago by Howard and group, which is a title that contextuality supplies the magic for quantum computation. So again, no entanglement, nothing, but it is something called related to contextuality, which follows from nothing but incompatibility of measurements. There are also other works, so on and so forth. So I would end with another slide. This is our work for again in 2023. So what we showed here that again you can have advantage through incompatibility, but whenever you want that advantage, quantum advantage to grow, that is the meaning of complexity, then the power is provided by quantum contextuality. Nothing else, no more and no less. And there are many such examples in quantum key distribution, random access code generation, random number generation, so on and so forth, where you can show that contextuality is something which is providing for you the magic. Okay. So thank you very much. Thanks also, Arun. So this is the summary. So what I've tried to highlight for you that there are various forms of uncertainty relation beyond the so-called textbook Heisenberg relation, starting from the work of Robertson Schrodinger to entropic, fine-grained, etc. And of course, there's a lot of interesting physical content of these uncertainty relations, which I did not have time to talk about. I just gave you a glimpse that they can reveal quantum correlations, their relation with non-locality, so on and so forth. And for any given uncertainty relation, you can find its application in quantum information processing, like some I showed you, determination of purity, demonstration of EPR paradox and steering, reduction of uncertainty using quantum memory, linking with the non-locality, so on and so forth, and also application of privacy in quantum key distribution. And finally, what I tried to highlight in the last part was the manifestation of uncertainty in quantum incompatibility and contextuality, which powers all your beautiful technologies this day. And I am very happy to end with a comment that quantum technologies have become so ubiquitous that I'm very glad to see their use even in such a deep spiritual domain like the Bhaktivedanta Institute, where you are organizing such beautiful conferences with the help of quantum technology. And in the coming years, you will be using quantum versions of your cell phones. So thank you.